Hello, everyone. Thank you for attending today's webinar titled How to Move from a Powder-Coated Finish to a High-Performance Powder-Coated Finish, brought to you by Products Finishing and presented by Vitracoat. I'm your moderator, Scott Francis, editor of Products Finishing. Today's presentation will last approximately 45 minutes, followed by a question and answer session. If you have a question, you can type it at any time during the webinar in the Q&A section of their chat. The webinar is being recorded and when complete will be made available to you via email from Products Finishing. And our presenter today is Steve Houston, Vice President and Business Director for Vitracoat. Steve has more than 35 years of experience in industrial coatings, from managing sales organizations to technical support teams to R&D groups. Prior to his work with Vitracoat, he served in direct roles for such companies as DuPont and RPM, and has also served as the Executive Director for the Powder Coating Institute. Steve, welcome, and I'll hand it over to you.
Thanks, Scott. Appreciate it. I'm going to speak loud so hopefully everybody can hear me. I've got a number of slides to run through today. And first, I wanted to introduce you a little bit to Vitracoat. We've been an organization that has supplied coating since 1948. We're privately held, the largest powder coating supplier to the Western Hemisphere. And my responsibilities for Vitracoat is North America. I have specific business director responsibility for the Americas and Canadian business. These are a number of our product brands that perform differently in different environments. And many of the names I'm sure that you have seen if you're in the powder coating world. We have a huge technical staff. We've got 14 different distribution centers. I'm currently at our Elkhart facility, which is our small batch manufacturing facility. And we have a Lerma facility outside of Toluca, Mexico, and another manufacturing facility in Colombia. So now that you know a little bit about Vitracoat, if you're not familiar, I'm excited to talk to you about really taking your current process and elevating it from a performance coating to a high performance coating. And there's a lot of ways that you can look at, but let me start with the idea that today we're going to talk specifically and exclusively about thermoset powder coatings. I put some things in here not knowing the experience level of the attendee. For those of you that aren't completely familiar or today aren't using powder coatings are very, very similar to liquid paint. It's a coating. The only difference is that it doesn't contain the vehicle or the solvent, the water in some cases. It has a resin, has the backbone, it has the pigments, the additives, all the components that make a durable coating are in the powder, but it's sprayed in the dry form, as opposed to liquid that has a vehicle or solvent that allows it to be sprayed in the liquid form. It's the organic polymers that are used, flow additives. If you want a specific look, you might have things that make it peel or texture. We can add metallics. Virtually any look that you want, we can get with powder coatings. And we'll do it in a variety of different ways. The Powder Coating Institute defines it as coatings formed by the application of a coating powder to a substrate. So the idea is you take the powder coating, you apply it to a substrate, typically aluminum or metal, an alloy of some sort, and then it's fused into a continuous film by heat or radiant energy. That's what makes it flow, cross-link, and give you your finished product. So that's powder coatings. So when I thought about this conversion or this idea of taking a powder coating, finish it, and elevating it, I first wrote the introduction that you've seen, the description of this webinar. And I want to focus on the bolded areas. We're going to talk about and have you kind of do a deep dive into what you're doing today, review that, and I want to also kind of stimulate your thought and give you some things to consider as you amp up what you're doing. Measure, reconsider, do a lot of different things and look at your particular application of powder coating today so that you evaluate the things that you can do to kind of turn it up or crank it up a bit. If some of you that have not used powder coatings before, this will be just as valuable to you as well as you think about some of the ideas pertaining to powder coating that might give you a little advantage or give you a little cut above what a normal process may look like. So when I thought about doing that, what I thought was that, well, how can I present it? Because we're not talking, there's not a lot of interaction. So what can I do to really focus on what I believe are some of the hot topics, so to speak? So this is what I did. I decided that what I'm going to do is I'm going to put out a blanket number of statements. And in those statements, they might be true. They might not be true. They might be maybe or sometimes. But these are common statements that I've heard in the powder coating world that I think deserve a deeper dive or more of an explanation. I think in every case, they can pertain to pretty much all coating applications, no matter what you're doing or what product you're doing it with. So I wanted a broad spectrum of topics, but I wanted to be able to do a deep dive in them. So what I'm going to do is I've put together, again, some statements. And I'm going to pause after the statement's made, after I read it, to let you think about whether or not it's correct or incorrect. And then I'm going to tell you if it's correct or incorrect, and then I'm going to tell you why. So let's kind of get started. Super durable. I'm sure we've all heard of the word super durable. We've all listened to it or seen it in print, looked at it advertising, looking on different product codes. But here's the statement. When you purchase a super durable product, you're assured exceptional weathering performance that will meet AMA 2604 specifications for weathering. The reason I put that statement in there is because I've actually heard that said. I've heard it said by salespeople. I've heard it at shows. I've heard people make that statement. Here's the reality. It's a wrong statement. As you think about your process and how to elevate it from where you are today to maybe a higher performance, if you're using a super durable or considering using a super durable, consider this. I can take virtually every one of these different chemistries and add a super durable resin to it. I can do it with the hybrid. I can do it with the aliphatic urethane. I can do it with the Primid non-TGIC. I can do it with TGIC. I can put a super durable component to the majority of these different chemistries. The problem with that is that it doesn't give me any extended durability. And what I mean by that is the resin, while it's the backbone of the coating itself, in order to make a super durable product perform exceptional or perform in a high performance way, you've got to consider every component in that formulation. Super durable is not a brand. It's not a statement of performance. It's not linked to a specification. It in and by itself will not elevate necessarily your weathering performance or protect against UV. It only describes the resin associated with the formula. The reason I say that is because it's been said too many times wrongly that, hey, super durables will meet certain specs, specifically AMA 2604, which is a 5-year spec. And that's absolutely not the case. I'll even go on a limb and say that I believe that most super durables in the market today will not meet AMA 2604. And then when you think about AMA 2604, the hard reality is, are we using the right organic pigments and inorganic? Are we using the right extenders? Are we using the right gloss control agents to meet that specification? Are we using the right additives? You see, as you have this melting pot of all of these ingredients for a formulation, as you look at different specs, that list becomes smaller and smaller. I can use an orange pigment that has great weathering, exceptional weathering. I'm a 2604 weathering. But there are a variety of different orange pigments that do not. They can give me the same color. And I use orange as an example. The hard reality is when you think about super durable, don't think about it as an end product. Think about it as a component to a product. We need to formulate for your specification. In our Innovation Research Center in Houston, Texas, we did a study. We did a study on how to formulate for super durable products. And of course, when you put in the highest performing pigments, you put in some of the highest performing extenders, you put in some of the highest performing super durable resins, we had very, very good high performance results. But even when we came down to the ratio of some of those ingredients, taking the same exact ingredients, but changing the ratio, that in fact impacted the weatherability of the product. So, how can you be sure that you're getting what you need? The reality is, don't just settle for super durable. Link your requirement to the product. You don't want super durable. You want a product that will meet a specification that you either write or is open in the market today. I'm a 26-4 is one I keep referring to because that's a very common specification. Why rewrite it if it meets what you're looking for? Super durables will meet that spec if formulated properly. You want to elevate your game? You need to write your specification that describes your performance needs. Elevate it in that way. Make it clear what you're trying to obtain in order to make sure that every product that you purchase from your vendor will meet that requirement. Whether it's hardness, flexibility, chemical resistance, UV resistance, weatherability, corrosion resistance, mar resistance. There's a variety of different characteristics that coatings can withstand. And if they're properly defined by you, the consumer, then you can have your supplier make sure that they meet that. So I'm saying here, a very simple process is write a specification around your product so that it's very clear what your product must meet. And if it says send me super durable, I guess the point is you're not really saying anything in particular. Here's the next statement. Zinc rich powder coatings will give you increased corrosion resistance over powder primers that do not contain zinc. Think about that one for a second. Zinc rich powder coatings will give you increased corrosion resistance over powder primers that do not contain zinc. Ouchie. Wow. That may surprise some of you. Here's the reality. First, you have to understand what the zinc is doing in the primer. The zinc is sacrificial. Its purpose, it's a hard word to say, to take the energy from the oxidation and absorb it in the ink. However, and this is a key element, you must have enough zinc to be effective. Small amount of zincs are simply spraying heavy coating without the zinc benefit. If I'm putting a very small percentage of zinc in the coating, I'm getting little to no benefit from the zinc and how it's supposed to function. Zinc-rich primers are unique from regular primers because they contain the zinc, and therefore they possess a highly sacrificial anodic property. High concentrations, and I've bolded that and made it red, high concentrations of zinc dust are sacrificial when in direct contact with steel by providing a cathodic protection and galvanizing property. So in order for a zinc primer to work, you've got to have enough zinc containing in the primer for it to work. Zinc rich didn't start with powder coating. Zinc rich is a very common phrase used with liquid coatings. And if you think about liquid coatings, it means that we're putting in a high in abundance of zinc in that formula, and we're spraying it using the vehicle of water or solvent that evaporates off, leaving that film which contains a very high percentage of zinc. 55% is probably on the very, very low end of what you need to be sacrificial in order to perform well. 70, 80, 85% zinc by weight. That's where you really get to the point to where it's becoming the cathodic result that you need from the zinc within the coating itself. You have to have enough zinc. I've seen zinc primers that have 13% zinc. The hard reality is all you're doing is you're spraying a very heavily weighted powder with very, very little benefit from the zinc itself. You might be better off just using an epoxy. This is what it looks like. If I take a side cut from the coating in layers, look at the zinc-rich primer at the bottom. It has so much zinc so that the zinc itself is going all the way through to the coating or to the steel surface itself. In this case, a grit blasted surface. That's when you get the benefit of the zinc within the coating itself. Now, powders, they don't have a lot of evaporation after it's coated, right? You're spraying it in the dry form. You can only put so much zinc in it. And 65, 70, 75% is probably going to be about the top you're going to get in a powder coating before it becomes so heavy it can't even be sprayed or fluidized. You see, if I've only got a small amount of zinc, these are 3 different coatings. Each of them perform and look the same. They don't perform the same, but they look the same. The one on the right has no zinc at all. The one in the middle has very little zinc, and the one on the left has enough zinc to give you some properties. The point is that while the zinc itself makes the specific gravity of the coating much heavier and you're getting less powder per pound, you need to have enough zinc to give its performance. The middle one illustrates that if I don't have enough zinc to give its performance, I'm just paying for something that gives me little coverage or a reduction in coverage because it's heavier. And the one on the right is just pure epoxy without zinc at all. So those are the same weights, but different amounts because of the zinc composition. So when you're referring to zinc containing, and I like to say zinc containing powders as opposed to zinc rich, when you're referring to a zinc containing powder, you need to have a specific gravity of 2.8 to really about 3.3 before you really get the added effectiveness of the sacrificial zinc component. So keep that in mind. It's pretty easy. I'm not asking you to go look at the zinc amount, but if you just get a gravity in the high 2s or low 3s, then you've probably got enough zinc to give you some performance that'll give you that sacrificial component. Think about that when you're thinking about using primers and using zinc containing primers. Corrosion resistance. So here's the statement. If you run a corrosion test on panels, you can be assured that you will accomplish the same, if not better, results on your parts. If you run a corrosion test on panels, run it through your pre-treatment system, you'll be assured that you can accomplish that same result from that panel as on your parts, if not better. Well, that's wrong. See, the thing about corrosion is that it goes through the path of least resistance. At least that's where it starts. What's pictured here right now in the top is panels run with an ASTM B117 standard. The one to the left has a huge amount of creepage underneath the scribe. The one to the right performed pretty well. The bottom right is a salt spray chamber where those panels were tested. The one to the left is a part that was tested with the same powder on the top right panel and performed horribly in the field. It's because obviously the panels aren't going to dictate or be a 100% representative of your part. Now, that's an obvious answer. I mean, I give you that one. There's also some more detail I want to go through. The reason that the part I showed earlier corroded really, really bad and the coating actually peeled off of it is because this is what it looked like when it came out of the oven, but this is what it looked like before it went into the coating booth. So you have to have a good representative of what the panel may look like. But I want to take this conversation another step. If you're going to test if you want to get an idea of how your part's going to maintain and hold corrosion, you need to look at all of the elements of that part. Corrosion starts at the most vulnerable areas where you've got the thinnest amount of film built. Poor pretreatment, Faraday areas, outgassing, even undercured powder. Those are kind of obvious, but where corrosion typically starts is on edges, shown here in this wire. That edge has less than 0.2 of a mil on it, while the wire part has over 3 mils. My corrosion is going to start on that edge. And in every part that you make, your most vulnerable area can be, in many cases, your edge, not being tested on a panel. As I look at this HVAC unit and you look at the flat areas on the corners, those are probably going to perform very well and similarly to a panel, but the louvers are going to be my most vulnerable area because it's hard to build film on an edge unless that edge is rounded or sanded or prepared well. And if the abundance of numbers of louvers here, that would be just totally too difficult, too time consuming. Think about these parts. A lot of flat areas, a lot of edges as well. The most vulnerable area on these parts is going to be that edge. So you want to test the part. You actually want to test your worst case scenario where I've got the sharpest edge or the most edge, and then spray those through your system. Clean those through your process. Paint those with the powder that you want to evaluate and put those in salt spray. Panels may give you a comparative data, meaning that if I'm running 500 hours on a B1000 panel and I use another coating and I want to compare it to that one, it can give you good comparative data, but only on the panel. At the end of the day, if you're not selling panels, and I'm sure you're not, you need to evaluate your part, or at least a part of that part that gives you a very harsh scenario for comparison. I'm not talking about colors, even though powder comes in a variety of different colors. I'm talking about comparing the area on your part that is the most vulnerable and can give you the most and quickest impact for corrosion. Edges, Faradays, those kinds of areas are most important to look at. That's what the testing should be tested for. Bonded. One of the benefits of bonded powder, which is a metallic coating, is that since the metallic is 100% encapsulated, there's no need for a clear coat. So one of the benefits of using a bonded technology is that the metallic in that formula is 100% encapsulated because of the bonding process, and therefore clear coat's not required. Wrong again. There's a number of ways to introduce metallic into powder coatings. You can extrude the metallic, you can blend, dry blend the metallic, and you can bond it. You can get some looks in blended metallics that you can't get in bonded materials. You can get some looks in extruded materials that you can't get in bonded. The reason for the bond is because what we're trying to do is protect the metallic, encapsulate it into the resin so that we get application window that's broader. If I have powder and I dry blend this heavy stainless steel metallic in it, they're going to fluidize differently. They're going to take on a charge differently. They're going to spray differently, and thus they can give me a different look. The application window is fairly narrow. The bonded idea is that we take the base coat, just like we would in a dry blend. We do manufacture it separately, and then the powder base coat and the metallic pigment are placed in a heated mixture that just softens the powder enough for the metallic to adhere or bond to the material itself. The thing here, or the misnomer, is that 100% of the metallic is not encapsulated. You want it to be a high percentage. You want it to be as high as possible. You'd like to reach 100%, but rarely do you get there. Therefore, you still have free metallic, or you still have metal exposed that's not completely encapsulated. And so when you think about the bonding concept, can I get any look with a bond? No, I can't, because of the limitation that it gives me in terms of heating and how it's blended. Sometimes a dry blend will give me a more metallic look. Are there metal compositions with 100% encapsulation? Through bonding, you do not get 100% encapsulation, so no. Does bonding give me a larger application window? Absolutely it will, because you're taking the metallic and you're blending it or bonding it with the other components within that product. And should I clear coat a bonded powder coating? Well, I guess to be fair, The answer is maybe. It depends on your application. If I'm coating a louver that's going to be in the ceiling where there's not going to be any traffic, no handling, no exposure to the elements, no exposure to UV, absolutely, I could probably get away with it because it's going to look like that for a very long time. But if exposed to the elements, if it's a high traffic area, if it's being handled a lot, a clear coat will absolutely enhance the durability of that even bonded product. So be careful. Bonding is a phenomenal way and a great way to get the looks you're looking for with a broader application window, but you still have to be careful because there's metallic in it that can be susceptible to things because it's free metallic. Film build. So the question is, if I just have one single layer, one coat of 4.5 mils, that's going to give me the same protection as if I put on 2.5 mils of a primer and then gel it in a 2 mil top coat. I mean, at the end of the day, they're both 4.5 mils. The answer is no. That would be a big no. And the reason is simple. As I mentioned earlier, spraying on edges is difficult. It's hard. The material itself, whether it's a powder or a liquid, doesn't want to hang on an edge. It wants to flow from that edge. And if your part has edges and I try to hang 4.5 mils in a single layer, I'm going to have a very difficult time getting good coverage on those edges. Well, let me try to illustrate what it would do if I put on a primer first and I gelled it and then a top coat on top of that. So if this square box is my part, I have 4 very sharp 90-degree angles or edges. If I put on that primer first and gel it, it's going to look something like this. A variety of different film thicknesses, but on the edge, I'm still very thin, even with my primer layer. Now, I can make that primer layer shorten gel so that it does hang better, perhaps puts on a higher percentage of the finished product on the edge. But I have this layer of coating with a tacky film that's gelled before I put on my top coat. So I'm going to build better and I'm going to build thicker in my most vulnerable area with this 2-layer system. So I put on my primer and then I put on my top coat, which in this case is the red. The idea here is that I want to build where I'm most vulnerable again. I want to build on those edges. And so the answer, if you put on a single layer at 4.5 mils or a dual layer with a primer and a top coat, I believe your protection dramatically goes up with that 2-layer system. Not to mention that I can define and design that primer to do things that my top coat may not be able to do. As I mentioned earlier, hang on edges because of the way it flows. Give me better adhesion characteristics because it may be an epoxy system. And then my top coat gives me my physical and aesthetic appreciation. I get the look and I can get the physical characteristics that I'm looking for in the top coat. So a 1 coat 4.5 mil will not give you the same protection as a properly applied 2-layer system. Well, now I'm having a little technical difficulty here. There we go. I also wanted to talk a little bit about what gel meant, just so you're familiar with what I mean by that term. On the far right hand or left hand side of the picture, it showed the powder and the particles laying on the substrate. And then as you subject that powder to heat, radiant heat or convection heat, it starts to melt and it starts to flow. And over time, eventually, it will completely cross-link, forming a film. The gel is in that melt and flowing section. I haven't cross-linked yet, but I've started to melt it so that my top coat or my 3rd layer will come on and even adhere to that primer layer, and then I can mono bake those together. So I want to take my primer to the melting and gel stage, and then when I put the top coat on, I want to take it fully cross-linked through all of the cross-linking stage. So that's what gel means as I talk through that process. Transfer efficiency. The statement is the type of application equipment you use is the single factor in determining transfer efficiency. So whether you're using a handgun from XYZ company or one from another company, that is the single factor in determining how well you will transfer your material to the surface. I probably didn't fool anybody on this one. No, that's not true. It's a critical factor. It's an important factor, but it absolutely is not the single most factor. First, let's talk about what efficiency I'm referring to. Because there's transfer efficiency, there's application efficiency, there's system efficiency. What I'm talking about today is first pass transfer efficiency. When a part comes by my guns, automatic or manual or both, how much of that material that's sprayed out of the gun is deposited onto that part? What percentage of the material coming out of the gun is deposited onto the part? There are a number of different variables that will impact that. And the reason transfer efficiency is important, specifically in a reclaim system, is because over time, the particle size distribution will move finer and finer because you have the optimal particle size that will attract to the part more readily. And then you have the breaking down of the particles as you're reclaiming them through the system. So I want to get as high a transfer efficiency as possible, especially in a reclamation system. Well, in a non-reclaim system, the value is different, but just as important. If I've got a 70% transfer efficiency in a non-reclaim system compared to a 35% transfer efficiency in a non-reclaim system, my cost doubles at 35% compared to 70 because only 35% is going on the part. So either way, whether you're reclaiming or not reclaiming, first pass transfer efficiency is very, very important. Our Vitracoat Innovation Center in 2020 did a study on transfer efficiency. We looked at all the variables or the most important variables that can impact transfer efficiency. And this is what we found. We found that gun selection absolutely can impact transfer efficiency. The nozzle that you use on the gun can impact transfer efficiency. The booth air velocity will impact transfer efficiency. The gun, the volume of powder or the velocity of the powder coming out of the gun will impact transfer efficiency. The voltage and amperage setting on that gun, of course, will impact transfer efficiency. The part geometry and the size or type of part, those are very key in impacting transfer efficiency. Application technique can and will impact transfer efficiency. And the ground, the quality of the ground can be a very important factor in transfer efficiency. Let me give you some percentages. We took transfer efficiency up to 70% and then took and made variables within that application. The gun selection had the least amount of impact to transfer efficiency. The red being the high end, and as we made changes in the left side, different guns, there was only about a 5% difference, 65 to 70%. The things that made the most difference was part, technique, gun settings, and the type of powder. Yeah, the type of powder. If you take a powder coating that has a composition of ingredients that do not take a charge very well, it's going to impact dramatically your transfer efficiency. If you've done a test at the Nordson lab or the GEMA lab or the Parker lab or Wagner, and you've come up with these results. And then you go in full blown production and you use a different powder that may be less expensive or higher gravity or different components. It's going to give you different results, everything else being the same. So powder can be a very, very instrumental and important piece in impacting transfer efficiency. In this case, over 20% difference. Application technique, huge difference. The part itself, whether it's the gun to part distance, how it's hung, the part configuration, wire goods as opposed to flat panels, huge differences. Every one of these will impact your transfer efficiency, but each one of these need to be managed differently in order to optimize that efficiency. So gun is important, but in our study, there are so many other elements that are more important and can impact your transfer efficiency in a greater way. So here's the statement. As long as you maintain exceptional process controls, you can expect the same field performance on your finished part. As long as you maintain all the process controls that you're asked to maintain, you can expect the same field performance on your finished part. The answer is no. I look at it like this. Where in the world is Waldo? It reminded me when I asked this question because it really depends on where that part is in the world or wherever it goes to be used. Worldly environments are dramatically and drastically different. Therefore, when a product is located in an environment, where the product is located or what environment the product is subjected to will dramatically impact its life. Let me repeat that. Where the product's located or what environment it's subjected to is going to dramatically impact its life. If my finished product A is painted the same way as my finished product B, but finished product A is going into an attic in a house in Tulsa, Oklahoma, and finished product B is going to be on a beach in Miami, there's a very good likelihood that A is going to last a heck of a lot longer than B. So link your testing to the environment that your finished product will be subjected to. Is it going to a beach? Salty air, salt water, high humidity? Is that where your product's going to be used? Is that where it's going to be set? Is it going to a snowy environment? Which snow in and of itself is high moisture, of course, but it's all the things that we do to add salt on the roads that give us that headache, that gives us corrosion and premature failure. Is it going to be a tropical rainforest where the product goes? Is that where my product is going to be subjected? Is it going to be a very harsh desert where there's no humidity, where there's hardly any moisture, but yet the UV is higher than anywhere in the world? This is a UV index for all over the world. The darker the red, the higher the index. Also, as you might imagine or have surmised, the closer to the equator. But if you look north in North America and South in South America, it's light, very, very light UV. In Europe, there's not a very harsh UV environment. But in northern Mexico and southern US and in northern Africa, that's where the most harsh UV rays are. That's why we do our testing in places like South Florida, to give us that most harsh environment for UV. So think about your product. In order to obtain a high performance coating, you must first understand the atmospheric condition your finished part is going to be subjected to. I can't just paint it really, really good and hope it works really, really well and just send it anywhere it might go. You need to create a process that will perform in that environment, whatever it is. So keep that in mind as you're thinking through the whole concept around what is my corrosion requirement. Now this one's a little I don't know, added benefit or added discussion, if you will. The statement goes like this: as long as you comply with Steve's advice, you can expect a high performance on any part that you powder coat. Now, we've gone through a number of different things pertaining to powder coating, and we've talked about them in a variety of different ways. So as long as you comply with everything I tell you, man, you're going to get a high performance coating on any part you coat. That's not true either. Let me tell you the reason why. You can put on the best pretreatment. You can select the best powder coating. You can apply it to the part in the way that you've been taught or trained. Every time you cure it properly, you have the right film thickness. The problem with that statement is that the part of it that you perhaps can't control, has the product itself been designed well for coating? We typically will design a product for durability, strength, aesthetics, those sort of things. Rarely do we think about, is it designed well to take on a coating, to protect it, to make it look better and last longer? Does our part have sharp edges? Does our sharp have very blind spots where I can't even see, hard to reach areas? Are there hard to impossible Faraday areas? Do I have welded components that are butted up against other metal, causing a Faraday or causing metal on metal? Do I have hanging concerns, draining considerations, critical areas that I can't reach or get to? That's where the design in and of itself becomes really important. If you want to elevate your product to a high performance coating, make sure that the product itself is designed well to take a coating. I took a picture of this fence. It's actually a neighbor that I had. And as you can see, the vertical pieces are welded on the horizontal pieces. Now, this is when it was just installed and it looked great. But about 6 months later, it looked like 10 miles of bad road because every piece of those vertical started to corrode. Red rust was coming through. There's no coating back there. There's no protection. It's just raw metal on metal. Look good, but a horrible design for coating itself. This is a horrible design. Now I have the vertical pieces inserted within the metal or the metal vertical horizontal pieces. And I'm welding the round pieces to it. It really looks great. It absolutely looks phenomenal on day one. But I can't get coating in those very high vulnerable areas to give me that protection I need. There's a lot of different ways to weld your parts, to design your parts, to punch holes in your part. For powder coating, or any coating for that matter, this isn't a good one. I've got tack welds. I've got open areas. I am absolutely certain that will start rusting between those welded areas very, very quickly because I can't get coating in there to protect that sharp edge. The right side, you've got a weld that has about a 12 millimeter height. On the bottom one here, I've got metal on metal where I'm already starting to rust before I even go to coating. The left one looks good. It's wire that has been welded together with very little weld slag shown. There's ways to do it to make sure that I've got a product or a surface that I can coat that gives me the best chance of protection. I don't just want it to look good for a little while. I want it to look good for a certain period of time, defined by my test parameters and knowing what environment that it may go to. This is another one. I'll give you a little close up. Every one of those round pieces are welded to either side. It's going to be very difficult for me to put a coating there to give me protection. And then again, my vertical pieces are welded to my horizontal pieces shown. I want to see things like this. This particular part is welded phenomenally and gives me a phenomenal surface to pre-treat, to paint, and have my best chance of success in terms of application and protection. So if I do everything right, I may feel like I've done the process right, but the part itself, the design of the part itself, might not be conducive for a coating, and therefore I could just fail because of that design, fail because of areas that I just can't coat and protect, which is what I'm trying to do with my powder coating. Got one more. Statement is, this has been the most informative, well-presented webinar I've ever been exposed to. Now that was a correct statement. I don't know that it was. It probably wasn't. But I really wanted to run through a number of different things that could help you look within your process, consider it if you're putting in a powder coating process, so that you could make good choices and good decisions as you go through that design or go through some of those upgrades. So thank you for spending time with me. This is my email address. Feel free to reach out to me, shouston@vitracoatamerica.com. I look forward to answering any questions for you that I may, and I hope that some of this has been helpful in whatever powder coating problems or issues you might be having. I'm going to turn it back over to Scott and see if he's got any questions that I might be able to answer. Scott?
Thanks so much, Steve. This has been a very entertaining and informative presentation. Was hoping the thing would pop up again.
Yeah.
We have a few minutes to open it up for questions. If you do have a question, use the question and answer panel in your chat. And as a reminder, the webinar is being recorded, and when complete, will be made available to you via email from Products Finishing. First question we have is, if my end product is going to be subjected to a large variety of environments, how do I write a spec for such a broad window?
Yeah, that's a good question. I didn't go into that detail in the presentation, but it's a great question. I'm glad you asked. It's not uncommon to not know where your product is going to be or reside. And what I would always recommend is that you give your consumer, your customer, options, a good and better option. This is what we always do for the general population of our products. However, Mr. Customer, if you're going to subject it to a very harsh environment, such as beach or rainforest or by a swimming pool with chlorine, then we would recommend that you use our higher end finish, which may include a primer and a top coat, and write a spec for both of those. It does a couple of things. Number one, it gives you the opportunity to offer that to the consumer. And if they choose your typical coating and aren't satisfied with the results, they had the chance to select that higher, more durable 2-layer system. It also gives you the chance to kind of get a premium for that coating because it costs you more to coat with 2 layers, but it'll give that customer a higher end product and something that's going to last longer, no matter what environment it's exposed to. I've even had some coaters go in and offer a good, better, best kind of scenario, so that they leave the burden, if you will, on the consumer to say, which one do you want? Because all of them will look good, but the better is going to look good longer, and the best is going to look good and be your best approach for the longest period of time. So write a couple of specs depending on the environment that product may go to. Great question.
What is the best way to protect against chlorine ambient?
Well, I think I just answered it, really. The reality is, when we have materials that are going to be sprayed onto a product, and then those products are going to be subjected to things like that can demonstrate or speed up corrosion, then what we want to do is we want to make sure that we give us the most protection we can. My recommendation would be that I go in with a primer so that I'm getting good coverage, good adhesion characteristics, an epoxy primer. Could be a zinc containing epoxy primer, and I've got good edge coverage, and then I come back with my top coat, and that'll give me the most protection that I can for even that environment.
Can you use an FBE powder for a primer?
Absolutely. FBE stands for fusion bonded epoxy, and fusion bonded epoxies have been around a long time. If you drive down the road and you see that green rebar sticking out of the bridges, that green is going to be an FBE, a fusion bonded epoxy, designed for gas transmission lines that they bury that same green or a maroon color is typical for that application. These FBE coatings, it's not uncommon for them to be designed to where they cure with residual heat as opposed to a post bake. So they're very quick. They're very fast in terms of cross linking. The reason for that is they're spraying big parts, big pipes. So the pipe can come in hot and you spray it, and then that residual heat actually cures as it goes out of the booth area. I say all that to say that not every supplier can develop a good FBE coating. We can, and there's many others that can, but FBE coatings are very, very broadly used for primer, and actually one that I would recommend. I think they're going to give you the best performance characteristics. That and when zinc is appropriate and works well for you and has the amount that you need to give you that sacrificial element, I think either of those would be very, very good choices for a primer in virtually any environment. Good question.
Can you reclaim a bonded powder coating successfully?
Can you reclaim bonded powder coating successfully? The answer is absolutely, with a caveat. So let me just kind of put it in perspective. So the bonded material itself, as I mentioned earlier, going through the process is a high percentage of it is encapsulated, and there is some of it that's still free. So when I spray that in the virgin form right out of the box, I get an appearance. When I reclaim that, I'm going to lose something. I'm going to lose some of my metallic. The reason I say maybe is because as long as you can clearly define what appearance window you will accept, minimum amount of metallic and optimal amount of metallic and maximum amount of metallic, however you want to define it visually, then you can reclaim bonded materials successfully. A bonded material will not reclaim as efficiently as a smooth product, a product not containing metallic. Because it has this heavy metallic in it, it's going to spray differently and it's going to reclaim differently. But one of the benefits of bonded is that now I'm encapsulating a large percentage of that metallic into my coating itself. A dry blended material is very, very difficult to reclaim, and I would never recommend it because you get a lot of fallout with that dry blended metallic. But in a bonding environment, a product that's been bonded, your chances are much greater. And I have seen it successfully done a number of times. But just be careful. It's not going to be the same look. You are going to get a shift in look. And your virgin to reclaim ratio needs to be managed, as well as a very clear understanding as to what's acceptable visually as you reclaim that. So the answer is yes. Just some things to look out for. Great question.
We do FBE and the parts are subjected to the elements. What would be recommended for UV protection to prevent chalking?
Well, FBE, as I mentioned earlier, is an epoxy, and epoxies have virtually no UV protection. I wish I had a better explanation or answer for you, but the only way to prevent that FBE coating from chalking is to cover it, tarp it, put it in an area where it's not subjected to the sun at all. You've got to make sure that you remove it from that UV element. And what'll happen if you don't, as you've seen, is the top of it will come white chalk, and then the sides and the bottom of it will not, because they haven't been subjected to or as much um, of the UV as the top. So you need to cover it. You need to cover it, and or just keep it out of the sunlight. It's the only way to do it. I wouldn't recommend coating it with anything, um, because you really are kind of defeating the purpose, and you're adding cost when it's not necessary. But if your product that's subjected to the UV does not have UV inhibitors or does not weather well, then it's going to chalk, and the only way to protect is keep it covered, keep it out of the sunlight itself.
If you are putting 6 to 8 mil of powder coating on a part, you coat the part in increments, say 2 mils, and cure each layer. How do you verify that the increment layers are cured properly?
Well, there's a couple of ways. So let's based on the question, I'll make an assumption. Let's say you're putting on 6 mils and you want to put them on 2 mils at a time. Elcometer and other equipment measurement organizations have the ability to measure the dry film of that coating, so that you can actually get a dry film reading and then put on a coat on top of that and a coat on top of that, so you can get those readings in the dry film way. If you're actually curing each layer, you can obviously measure that after it's cooled down, and you can get a measurement there. If you're gelling that layer, the only way to do it is with your dry film equipment. And look at those, because you read the dry film, and then there's a formula built in, because you're going to get some loss of film, some mass loss during cure, and make sure that percentage is right. But they work really, really good. When they first came out years ago, they were pretty expensive, but I think they're very reasonable now and can be a really good tool for that, especially if the measurement of those layers is important. The other thing I'd ask you to do is, when you take measurements like that, measure in the same areas as you add layers. You have to do that in order to get an understanding of what 1 + 1 equals. And so you have to make sure that you're pretty precise in wherever you're measuring on that part.
Okay. Today I'm dealing with a lot of blisters on parts that we are processing. They show after the curing process. Um, I would like to hear any recommendations you have to help this issue before processing parts.
Well, not seeing the part, it's a little difficult, but I appreciate you defining it. A blister to me is something that where the coating itself is pulling away and bubbling up. A crater is where it's pulling away and it's more concave. And those are two different things typically. The concave is where I'm trying to really mold around maybe a contamination on the surface. And the blister is where something's trying to come out of my coating, forming that bubble. So I want to make sure that I'm talking to you about the right definition. In both cases, however, it can be a couple of things. Usually, it's going to be a contamination on the surface that, when it's subjected to heat, is blowing through or trying to burst through the coating itself. The way to test that theory is take your part, clean it, and then really take some MEK or something, an acetone, and clean that area really, really even better than you normally would. And then run it through your pre-treatment and see how, if the blisters are minimized or reduced. That just tells you that you've got to do something more than what you're doing for cleaning that area. But if the coating itself is going to have a crater or a blister, something's causing that. Now, the other one I was going to say is that if it's on a casting, well, that can be a variety of different things, and most likely it's an outgas. The casting is going to have pores within it that will contain or trap air, oils, water, and when it's subjected to heat, those need to come out and burst. And there's other ways to do that to minimize that or reduce it. And that is to preheat that casting before you go into your application and is higher than your cure temperature so that you're trying to outgas it before you put on the coating. So hopefully one of those fits what your situation is.
Is hot coating a good option for items with tight spaces, or is there a better way to coat them?
It's a very good option. If you think about the way the hot part works, in an ambient part or a cold part, I'm spraying on this dry film, and my particles are going to go through the path of least resistance. They're going to find ground, right? And so if I have a concave or a tight recessed, they don't want to go there. They want to go to the closest ground. If I've got a warm part, and I will say warm over hot, and I'll define that in just a second, then what happens is the coating itself starts to melt. And now I'm kind of blending it in where my particles, as they hit the coating, are going to stick. And I can get much better penetration into those spaces. Caution, if you only want to put on 2 mils, you're probably not going to do it with a hot part or a warm part. You're really starting it. It's going to build film really, really quickly. Now, hot to me is 250 above boiling, 300. I would not coat the part at that kind of temperature, but around 120, it starts to get warm. 140, 160. Those kind of temperatures really can benefit you when you're trying to do a couple of things: penetrate Faraday areas, get a really smooth coating if you're dealing with a high gloss material, and it can help in some cases with edge coverage. But it does work, and it helps a lot. You're just going to put on more coating than you're used to.
Can you explain how the air humidity affects the application process?
Yes, too high is bad and too low is bad, and I'll tell you why in both cases. Powder coating itself is hygroscopic, so that means that it absorbs moisture. And the way that you apply coating is you're putting out this corona field of charge, and the particles are passing through that. So in a high humidity environment, I've got the product itself trying to fight with the moisture in the air. In a low humidity environment, I've got the charging mechanism having no moisture to assist me in charging those powder particles. So really the place you want to be is between 40% humidity and 60% humidity. And I know it's a narrow window, but you get below 40, down in the 30, absolutely in the 20s, you have a hard time building film because you have a hard time charging. You get in the 70, 80, and 90 range, and sometimes you can have too much moisture. So 40 to 60 is the best, but 80 to 30 is more common in a pretty broad window. But moisture, humidity, both ways, too much and too little, can have a negative impact on your application. The key, though, is you want consistency. You don't want 40 one day and 80 the next because it's going to spray different. So that's why we talk a lot about having a climate controlled environment. If nothing else, it's a variable that I'm maintaining consistently so that I can maintain a consistent application.
Okay. We have a few more questions, but we're at the hour, so I'm going to ask one more, and the others, Steve will be able to get back to you offline.
Absolutely.
If we put multiple layers and cure, I'm wondering if we are over baking the first layer.
So I'm guessing what you're saying is if I gel the first layer and then I may gel the second layer and then I cure it all together, am I over baking the first layer? Typically not, because that hasn't seen its cross-linking temperature. So you want to melt and flow, and then mono bake them together. Now, if that surface sees 400 degrees, even for a short period of time, and then it sees 400 again and then 400 for 10 minutes, it's going to overbake. But most coatings are going to give you 100% overbake, which means that at 10 minutes, 400 degree cure, I can go 20 minutes at 400 degree cure and not harm my product. That's pretty typical. And we usually formulate to that. There's some products that I've seen, they can be 200%, 300%, 400% overbaked, believe it or not. But I don't think you're going to harm it if I've defined what you're trying to accomplish correctly.
Well, Steve, thanks so much for the presentation today. This has been great.
Thank you, Scott. Appreciate Product Finishing for putting this on, and all those that attended. Thank you for your time.
I'd like to also thank everybody for taking time to join us today. We really appreciate you being here and taking the time for it. We hope you'll join us again for the next Products Finishing webinar. For more information, visit pfonline.com/webinars. And have a great day, everyone. Thanks a lot.
Have a great day, Scott. See you, man.